Okay, so let's look at some homomorphic encryption where we can add encrypted values together. Okay, so this is the method that we use for homomorphic encryption. What we actually do is that we take our values, such as for Bob and for Alice, and then we cipher them, and then we can operate on them either with a logical function or a mathematical function, and then that should give us a ciphered result. So the advantage with this is that we can protect our original values but still operate on them. So in a world where we need to make sure that our data is secure, then obviously to work on encrypted values rather than the real values has great advantages. So some of the questions that we might ask is Bob older than Alice without Bob and Alice having to reveal their age? Also, if Bob has worked a number of days and also Alice has worked a number of days, how could we calculate their total income without actually revealing the number of days that they've worked? And also, how can we find out Bob and Alice's total income without actually revealing each of their incomes? So this is a major challenge for us in the software that we create, and we'll see how homomorphic encryption allows this to happen. So there are several methods around for homomorphic encryption, but many of them just provide partial homomorphic encryption. So RSA allows us to be able to add two numbers together, but it doesn't do things like divide or subtract. So with this method, the DGHV method that was presented by Gentry et al., what we have is we have our values, and then we have a secret key, and we can then cipher each of the values and then put them into some function, and we get a cipher output which can be given back, and we'll use the same secret key to be able to decrypt the value back again. Okay, so in this way the data processor here will never be able to see the values which are being enacted upon. And the way we implement this is with cipher bits. So what we do is we'll take, say, integers, and then we'll convert them into bits, and then we'll cipher each bit one at a time to produce a cipher bit. So here we have cipher bits, and it's not possible if someone is observing here to be able to determine what the actual original cipher bit was. We then feed this into a circuit made up of XOR and AND gates. This XOR is equivalent to an add, and this is equivalent to a multiply. So we take values, and the values here are very large integers, and then we operate on them with the logical functions of AND and XOR, and we should be able to create our output cipher bits here. Once we create these, we apply a secret key in there again, and we get the original bits back, and from there we can actually convert that back into our result. So this could be a subtraction circuit, or a comparison circuit, or multiplication, or division. We can create our circuits as we require for our application. And so the method that was proposed is this one here. So the mathematics behind it is that we take our single bit here. So this is our single bit M, and that's a 0 or a 1. We then take a random value, that's adding noise to it. After that, we create our Q value, and our Q value is a random number here, and it's randomized for every bit that we're going to cipher. Then we have our secret key, which is P. So this becomes our secret here. And P needs to be an odd number. Okay, so the functions that we have, the basic functions, XOR is not A and B, or A and not B. Okay, so it's a basic adder. Remember, we're only really interested in the least significant bit. A not, we invert the least significant bit. An and is equivalent to a multiplication in this method, and an or is equivalent to an add. And this works because we're only looking at the least significant bit. If we want to take a value and split it into its bits, let's say, and we'll split it into 8. So this creates a list with 8 zeros, so 0, 0, 0. Yeah. And then we take the value and we mask off the least significant bit, so that gives us the bit there. So now in the position 0 we'll have the least significant bit. We mask off with a mask of 0, 0, 1, 0, and we shift the bit down to give us what that bit is. We'll mask with 4, move down 2 places, mask with 8, and move down 3 places. So this is just a simple 4-bit conversion, but we can easily do the same for 8 bits or 16 bits. So the cipher itself takes the bit and then takes the secret key that we've created. It then creates a random number of Q and R, and then does this calculation that we saw here from there. Okay, so there's P times Q times 2R, and then plus our integer. And if we want, we can also in Python return back the value of Q and R if we need to use them, but we can discard them because they're not used anymore. They are really just there to provide us with some noise. So let's see. We'll look at our code in a little minute. Okay, so let's construct an adder circuit. So with an adder circuit, we often start off what's called a half adder. So a half adder is basically just our bits like this. Okay, so that gives us that gives us that. And so that's for our sum. And then we have carry. So for the carry, 0, 0, 0, and a 1. Okay, so when we get a 1 and a 0, it gives us a carry forward. So if you think about it, 1 and 1 gives us 0, carry forward 1. So this becomes our carry forward value, and this is this one here. We have the sum and then the carry forward. So if we work at the logic, this is like an XOR circuit here. So that's the logic of an XOR circuit. It's A bar and a B, or A and a B bar. Okay, so we've got to break it down into simpler logic. And the carry becomes A and B is our carry. Okay, so that's the carry there. So in Python, if we take 2 bits, then our sum becomes the XOR, as we've seen the function that we used before, and then the carry out becomes basically the AND function, or the multiply, and we can return back the sum and the carry. Okay, so this is a half adder, and the half adder only does one sum for 2 bits and produces the carry out. A full adder looks like this. So we take the half adder circuit. So we take the half adder circuit here and here, and then we get an output here and a carry out. So if we take A, B and a carry in, so if we go through this, then we'll get this. Okay, so 0, 0, 0, sum and carry out. Okay, so 0 add 0, 0, that's a 0, that's a 0, and sorry, that's a 1, that's a 1, and a 1 and a 1 gives a 0, and we carry out 1. This will give us a 1 here and a 0. This will give us a 0 and carry out a 1. This will give us a 0 and carry out 1. And this will give us 1 and carry out 1. Okay, so that gives us our basic table that we're looking for. So it's equivalent to when we're adding and we bring in a carry. So in this case it's 1 add 1 add 1 is 1, and then carry forward 1. So this becomes our carry out here, and this becomes our carry in. So we can remodel this with the sum and the carry. The sum and the carry here is this one here, and then we can feed these outputs here into here, and then we take our carry in for the second half adder, and this will give us our sum. Then for our carry out, it will take the two carries, this carry, an intermediate carry, forward, and then this other carry here. Okay, so the two carries, carry outs, will then go into here, and we do an OR operation or an add in our cipher. Okay, so this is the Python code. We take 2 bits in and a carry in, as we have here, and then we'll put it through a half adder. We then get the sum out, which is here, and feed that into the next half adder. We'll take C in, we'll feed that one in there, and then this time we get the overall sum out for the full adder. And also get another carry here. We'll then take the 2 carries from the half adders, and that will give us our carry out. And then in Python we can return the 2 values back together. Okay, so that's a full adder circuit. If we now keep building this up, this is what a complete adder circuit will look like. So in this case we've got 8 bits going in for a value of A plus B. Okay, so we convert to each of the bits, so we've got A0, B0 and so on. So they go into a full adder, and we bring in the carry in, and that will give us a sum. We take the carry out here and then feed that into the next gate, take A and B and so on. So that's a 2-bit adder, and this is a 4-bit adder, and then this is an 8-bit adder. So we can build them up in stages here. So once we've ciphered our values, so these are the cipher values for A and B, and we take in a carry in, then we can use our full adder to give our outputs here. We then take the carry out here, feed it into the next stage, get the result, feed that into the next stage, get the result, feed that into the next stage, and so on. So in this way, we're creating our cipher. So let's look at the code. Okay, so let's look at the code for this. So in this case, this example here, so we're feeding in a value of 6 and 3. So we get a result of 9. That's a 1, no 2s, no 4s, and an 8. Let's try 6 and 5 should give us 11, an 8, a 2, and a 1. Okay, so that works. So this is the conversion here into our bits. So this is the least significant bit, and then so on, and we've put it into 8 bits. Okay, so the code that we have is this here. So initially what we do is that we generate a random number, very big here. So this is our secret key, shouldn't really be guessable. We can then cipher Cin, which is a carry in, which is just a 0 anyway, and we put it through our cipher function. We can use P and Q if we want, but we only really need carry in. Okay, then we'll cipher each of the bits with inside the values. Okay, so we have a function here that converts the bits, and then we'll have cipher values here. These cipher values for the bits will be large integers, and they go into these functions here. The carry in becomes the carry out, and that goes into here, and so on. So we're using cipher values. At the very end, to be able to decode them back again, we need the value of P. So P we do a mod for, and then we're only interested in the least significant bit, so we just take that bit off. So then we can calculate the sum here and the carry out, and then we can end up showing our sum values and our carry out here. Okay, so here's the example here. So you can see our sums become very large numbers, mainly because we're putting in a very large value for the carry out, so it becomes much larger. Okay, so you should be able to try different values here. So there's another one. So 2 and a 12. That's an 8, a 4, and a 2. Okay, that should make this bit go, and so on. Okay, so in this way we can actually preserve the original data, but be able to create any function that we require. Okay, so that's a demonstration of homomorphic encryption with a basic 4-bit adder. Okay, thank you. All right.